introduction. And hi, everyone. Thanks for coming. It's great pleasure to be back. This is like coming back home to me. And also it's great to see people like my advisor and teachers, mentors, also faculty, students, friends in this room. Um, for today, I'd like to give a talk about our team's work at Amazon Alexa. We focus on the acoustic event detection. For my talk, the first part, I will give an introduction on Amazon Alexa and Echo devices. After that, I'll be talking about acoustic event detection, including the Alexa Guard, which is a new feature we launched, which is also the first AED-powered feature for Alexa. After that, I will be giving an overview of several recent publications from our team at the speech conferences. Let's go to the first part. As you may know, speech has been an important area in the industry, and Amazon has been investigating heavily in this area since recent years. This slide summarizes a list of products supported by Alexa speech and language technologies. Here we have different types of devices, including Echo, we have Fire TV, we have tablets, or even newer version of Echo devices which has screens on it. And there is it's a longer list with new devices added from time to time. Here, what is Echo? Echo is the flagship device for Alexa use case. It's a speaker which has a pair of microphones of the speakers, which gives high quality sounds so that it could be used to play music, also to broadcast news or have conversations with users. It also has a microphone array on top, which enables it to listen to our customers even in very challenging acoustic environments, and even the customers is speaking far from the Echo devices. For designing Echo, we follow a few philosophies. First, we want to keep the device to be as simple as possible. For the ideal case, we want the Echo users to be able to talk to Echo devices as naturally as they talk to any human persons. And there, we want to reduce the frictions as much as possible. We also want to implement the features in cloud when it's possible. In this way, we have more resources in cloud to run all the features for speech recognition, for language understanding, dialogue. We are also able to roll out new features on a faster pace for cloud. We also design our device and applications to be mutual agnostic. Regarding the Echo device, there are several features running on it. We have a record engine running on local Echo device. That means this Echo will be only triggered when our customers speak the word Alexa. And it also has beamforming to point to a specific direction where our users speak from, so that they could better understand the people's voice and increasing the recognition accuracy. It also has echo cancellation functionalities to remove the interference from the sound generated by Echo devices themselves, like music play or like the broadcast news. When the local device gets triggered, there's the audio stream to cloud for further processing, like mentioned, for speech recognition or language understanding. Echo device also has Bluetooth plus Wi-Fi connections. Here, what is Alexa? Alexa is the voice assistant sitting on Echo and in cloud. You could think Alexa as the brain of Echo devices. It learns to better understand people's voice commands by interacting with users. Alexa has many different functionalities. For example, it could tell the weather. It could play music, answer questions, and it also helps with order pizza, order Uber, etc. We also have more functionalities added to Alexa on a daily basis. Here, I will quickly go through a simple use case of how Alexa works. The idea is if our customer wants to ask the weather information, first they will speak, Alexa, what's the weather? And this record Alexa will be taken on the Echo device, And from there, the user's utterance will be streamed to cloud. In cloud, we have a central control platform which connects to different modulars. The way how it works is first, it sends the audio to speech recognizer and getting its output and feed this into a language understanding component. From there, this LU component would recognize this is the intent for weather information. And sometimes it also recognizes the name entities or slots to provide more useful information. After that, the speech controlling platform will cause the skills or applications which is designed for providing weather information, and it extracts the information and also gives a speak directive to the text-to-speech component. From there, TTS will generate Alexa voice and telling the weather information, which will be played on the Echo device. And from there, Echo will be, or Alexa will be speaking back to users telling the weather information. As you may see here, Echo Alexa are mainly designed for human voice recognition and understanding. And here, our team works on acoustic event detection, or AED, which provides Alexa a new dimension of functionalities to be better understanding the surrounding environment going beyond listening to only human speech. In real world, there are so many distinctive sound activities. For example, there's baby crying or car crashing, gunshot, dog barking, and many others. AED refers to the technology of recognizing the sound events, giving the input audios. It can be very useful in improving people's lives. Here are a couple of examples. It could be used to improve the caregiving qualities for a group of elderly people or for people in recovery. There has been efforts on building a system combining AD technologies as well as the ultrasound receivers to actively recognize those clinical relevant events. For example, cooking, walking, or people falling down. By building an accurate recognizer for those sound events, the system could be able to better monitor the elderly people or people in recovery's daily routines and be able to tell an anomaly if such things break up. Another example of AD use case could be for self-driving cars. And so far, the most efforts on building the self-driving system have been focused on the improving the vision. But think about this. If we could enable the self-driving system to not only see what's happening on the street, but also listening to the environment, like the sound of honking or siren or tire skiing and motorcycles, that will provide those self-driving systems more information to make more intelligent decisions on which direction the car should be going. Given all these potential use cases and considering that Echo has a microphone to pick up the audios, and also it has resources on device and in cloud to running machine learning systems, that makes Echo Alexa a perfect platform to deploy AD technologies. Here's what we came up with. In May this year, we launched a feature called Alexa Guard, which is the first AD-powered features at Alexa. At launch time, we support two sound events, alarm sound and glass breaking. This feature is designed for improving the security of the houses. And before going some details of Alexa Guard, I'd like to discuss a few challenges for building this product, which also influence our system design. First, we have the Guard system running on device, and which has very limited resources. But that means we need to build a high accurate AD detector, which consumes limited CPU and memories. Another challenge is, at the launch time, we support two sound events, alarm and glass, but we want to build a system which can be easily scalable for supporting more sound targets. When later we want to add more sound events, we could quickly add them without significant more effort and without significant increase of system complexity. The third challenge is that different sound events may have different time durations in nature. For example, a glass breaking sound may last for a second or two. The alarm sound would last for a minute or even longer. And how to build a system which could accurately recognize different sound types, which last for different durations, that has been another challenge. And at last, we also want to have very high accuracy. As this feature is for home security purpose, we want to build the system to have extremely low false eject rate. That means if there's such events as alarm or glass breaking happening, we do want to pick them up and send the notifications to our users. On the other hand, we also want to have extremely low false accept rate, which means if there's no such sound events happening in the real life, we don't want to send false notifications. Having all those challenges in mind, let's quickly go through the system architecture for Alexa Guard. The idea is that when our customers leave their houses, they could turn on this guard feature. From there, we have a detector running on local Echo devices, which start to listen to the sounds from glass breaking or alarm sounds. If such sounds happening, and these local devices will get triggered and also stream a audio snippet to cloud for further verification. In cloud, as we have more resources, we are able to build a larger and more accurate verifier to double check if those audios indeed contain the target sound events. If that's the case, Guard system will send a notification to our users' phones and telling them there's potentially alarm or glass breaking sounds happening. And from there, our users could listen to the audio streamed to cloud. They could look at the whole history of Guard detections. They also have the options to delete those audios to have their privacy protected. As you may see here, essentially we leverage a hybrid system with two stages, including both device and cloud. And this is similar to how we do for Alexa wake word detection. The idea is we want to run a very small footprint system on device to reduce most of the negative audios. But for the few or very tiny proportion of audio streamed to cloud, we have a much more accurate system to double check to reduce all the most of the false accepts happening on device and maintaining most of the true accepts. In order to build a high quality production system with AED technologies, there are different important components. And we spend lots of time optimizing the model architectures and the model training procedures. Another important part is about data. As you may know, for all the modern era machine learning systems, the data has been a key component. We need lots of high quality in-domain data to teach our model to learn, recognize those sound events. We also spend lots of time optimizing the engineering side on the system. We want to automate our whole model pipeline, including data ingestion, model training, deployment. We also have engineering teams to optimize the system running both on device and in cloud. Here, let's take a deeper look into the model architectures we run. Here, this part shows the device model architecture. The idea is, given this input audio, we first extract the acoustic features. Here, we extract the standard log mail filter banks, LFBs, and feeding those acoustic features into an embedding system. Here is made by the long short-term memory networks, which is powerful for modeling temporal information. Once we have the embeddings from the FPM modular, we will feed them into our predictors, which is feed-forward neural network layers, and with sigmoids as the output functions. Here you may see that we leverage a multitask for infrastructure here. That is, for each target event, it has its own output functions. The high values from the sigmoid output indicate it's more likely that the input audios contain the target event. By doing this, we can scale this system easily. That means if we have new sound events added, we are able to quickly add a new predictor with its own sigmoid output without changing the architectures of the LSTM modular, which consumes most of the computations on device. We also design our system in a way that the detections of alarm and glass are independent. That means if there's input audio contains both sound events, our system will trigger for both. Once the device system triggers, for example, for alarm, we would upstream these audios to cloud for further validation. And in cloud, as we have more resources available, we are able to build a larger and more accurate system. Similarly, we are given the same audio. We also extract the acoustic features here using FBEs. As we have more resources, we are able to extract a more refined dimensions for the FBE and fit them into a larger embedding extractor. Here we use a deeper convolutional neural network with residual connection. Once we have the embeddings from the convolutional neural network, we feed them into predictors and give it the output. Note that one difference is in cloud, we build a separate cloud models for each sound event, such that the problem space is further reduced for each cloud model. And this also helps improve the accuracy of cloud verification. Yeah. Oh, sorry.
So for this hybrid model, I assume when you want to optimize false positive, when it's false negative. So how do you think about the right threshold?
Right.
Go from one to the other?
Yeah, that's a very good point. Here that requires some empirical tuning of all the systems as well as our target. Typically, we have a targeted false reject rate. And from there, we could optimize the threshold on the device. But here we could tend to have slightly more false accepts on device, just making sure we don't miss those audio events, and we rely on cloud model to reduce most of the false accepts. So our customer won't receive those false notifications. But on the other hand, there is also a requirement to protect the privacy of users. So we cannot reduce our device threshold to be too much, to not allow too many audio streams cloud. It's not necessary. Yeah.
This applies both to the AE and to the vapor detection.
Yeah, it's similar.
You have 7 microphones.
Yeah.
You do this LSTM, the beamformed version, or do you feed it the raw waveform from one of those?
Yeah, here we are doing the beamformed version.
So it's already doing the beam. So, yeah. And in your experience, beamforming for these sounds is no different from the normal beamforming you do for speech. Basically the same algorithm works with it.
Yeah, that's a good point. Typically, the beamforming is tuned for human speech. And this may not be performing very effective for AD perspective. But this right now, the beamforming audio is what we see from our engine. And that's how we use them to pick up the to fit to LSTM for AED and record as well. But in future, it would be interesting topic to investigating using the raw microphone audios to see if that could further improve.
And the second question I had was that the feature extraction that you do,
yeah.
Is it then the same feature extraction that you do for speech? I'm thinking that speech things probably have a very different spectral representation.
Yeah, indeed.
Spectral density.
Yeah, indeed. For the sound events like glass breaking or this alarm sound, it could be narrowband, not as speech. But right now, this is what we use. But it could be interesting direction of exploring the feature side, like taking the raw waveforms or even more raw features and asking the neural network to learn as well, following some training the speech recognition as well.
So is the reason that you wanted to not mess with the other part of the device? What's the consideration that you're doing?
Yeah, that's the concern. That's the consideration for designing like this. We want to leverage as much useful or existing features possible to quickly build up this feature and which satisfy our requirement. Yeah, given this device and the cloud models, we also leverage a temporal aggregation approach to further reduce false alarms. The idea is that we know the alarm sound typically run for a long time with repeated patterns of 3 beeps. Given this knowledge, we could allow our system to listen to this alarm sound for a longer duration, like 20 or 30 seconds, to making a more confident predictions after observing the repeated 3-beat patterns. This has been a very effective approach of reducing false triggers. For example, there could be some security panel which gives its isolated beeps but has similar 3-beat patterns. With this temporal aggregation, we could effectively reduce all the similar false triggers from those security panels. And as mentioned earlier, a key part of building this system with high quality is to have a lot of high quality data. I have been asking about the question, how do we get the data to build the system? As you may see, this alarm or glass, they are rare events in the real world. And at least I don't remember when was the last time I saw someone actually break a glass. But to answer this question, we actually break those glasses. The idea is we actually spend money, we license contractors to break different type of glasses using different tools and in lab. So that we could collect the authentic sounds for glass breaking. Similarly, for alarm devices, we also purchased the most popular devices in the US market, and we trigger those devices that use echo to record. There are different ways of triggering the alarm sounds. For example, you could use the testing mode, but that's not exactly the same as the real alarm sound. So our data collection team also using some spring devices to trigger smoke alarm. Here, as you may see, this data collection process has been very expensive, and it can take a long time. Besides what we have, we also do the data augmentation technique to scale up our training and testing data. Here we tried a couple things. Once we could mix the positive audios with different negative audios. By doing this, we could easily scale up the positive training data with different background varieties. Another augmentation approach we use is we built an initial glass breaking detector, for example, from the authentic glass breaking sounds collected in lab. And we ran them on the audio part of our movies collections. At Amazon, we have an in-house Amazon Instant Video collection, and we mine those glass breaking audios from that movie collections. And here's a couple of examples from the data mining. We could run this process iteratively. That means we could build an initial glass breaking detector, which may not be very accurate. But the point is that we want to run this on a large amount of audio clips, and we select those audio clips which this detector gives high confidence scores. We could send those clips to our human annotators for double verification. After that, we could use the human verified audio, adding back to improve the glass detector. We run this process multiple iterations to get more and more higher yield rate for data mining.
Question.
Yeah.
Do you also perform the zoom in pulse response applied to convert it to for the data augmentation? Because your use case is always far field,
yeah.
And it depends on the room. The room in pulse response will be very different. So
yeah.
You have some comments about that data augmentation.
Yeah, that's a good point. We did experiment with that part. We augmented those with room impulse response, and we also have the testing data in the similar way. What we observed is that, yes, in the matched case, there's improvement, but for the other sounds, we collected in the real world or real rooms, which is not necessarily always the case. It could be the approaches we try, we didn't fully optimize. It could be like that. Yeah. Yeah.
For movies, you have very artificial sound effects in movies. I don't know how real they actually are. They might map to our notion of what a glass break sounds like, but maybe not real.
Yeah, I see your point. Indeed, this difference is from the medium play, but right now it's really hard to even for our system differentiate it's medium play or not. So for us, that's still valuable use case and for detecting, for making the training data as well. Yeah.
So once I listened to interview with Bezos, and he was saying, Alexa, 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 my Alexa was going bananas. I wonder if I watch the movie where people are breaking a lot of glass, if then there will be a lot of alarms.
Yeah, that's a good point. There's a similar case as WeakWord. WeakWord use some like fingerprinting to deal with these issues. But for AED right now, our use case is when we target for people not at home. They need to explicitly turn on this feature when they leave their house. So right now, this is not target use case, but eventually we may need to face this issue. And
That's what I did. I switched to Alexa when the boss was talking, so I told you the same.
Okay. Yeah, and here is a plot of a roughly 3 months beta run. The idea is we built our initial model and we deploy it to a beta program, which contains Amazon internal employees. And you see that at the beginning, the model performance is not very good. This measures the false accept rate. But the idea is once we deploy them into beta, and we collect those audios from beta traffic and do the human annotation to improve the model updating. From there, the model learns from correcting its own mistakes. And we see that this false accept reduces every time there's model updating. And in this week, we also introduced the temporal aggregation approach, and which further reduces the false alarms for glass to be almost zero.
Can you say
Yeah.
what the most common false alarms were?
Yeah, previously there could be some like security panels, like I mentioned, those could be beeps, but faster 3 beeps, or there could be continuous beeps spanning the whole 10 seconds with the same difference. And for alarm pattern, that's just a close 3 beeps and some pause, and then another 3 beeps. Those would give triggers.
And are you allowed to tell us what the y-axis is?
Yeah, I'm only able to tell the relative reduction of the y-axis, but not absolute numbers. Sorry about that. Yeah. But that's an extremely low number we are happy with, so we deploy to production. Our customers are actually using them. Yeah. It's not 0, it's slightly above 0. It's not 0. That's why we still have our work pre-check. Here, since the launching of the Alexa Guard to all the production users, in May we have been receiving very positive feedbacks from media and also from the customers. Here are a few examples. But the best feedback I like is always from the actual users. And for example, here is a quote from a Reddit post, which clearly tells Alexa Guard helps protect house. And the phone screenshot was also posted, which is included on the left side. And at Alexa, we built the state-of-the-art industry systems to provide the best experience to our users. And meantime, we also investigate on the technologies to push forward the frontier of AED research. For example, this slide summarizes publications from our team at recent speech conferences. As you may see here, we spent efforts doing the detection of real sound events. We investigated on new model architectures and optimized neural network training. We also deal with the data sparsity issue for the real sound event. As mentioned earlier, we have a detector running on local devices with limited resources. Hence, model comparison is an important topic for us as well. We also did some work on the medium presence detection to tell if the audio is from medium play or not. And recently, we had a side research project on the spoken term classification. And it's worth noting that a significant proportion of those work initiated from our internships. Our team has a very solid record of hosting interns doing interesting and impactful research projects. For the remaining time, I'll be focused on discussing these following aspects: how to deal with the data sparsity, how to do the model comparison, and our work on medium presence detection, as well as for spoken term classification. For data sparsity, the issue is that here we deal with this real sound events in the real world, which means which impose a inherent challenge in that there is very limited available in-domain data for building the accurate systems. To deal with this case, we try different approaches. One is semi-supervised learning. The other one is based on embedding. For semi-supervised learning, the idea is we want to leverage the large amount of unlabeled data to improve the model building with limited labeled data. For our experiment, we leverage a public data set which is called audio set. It has a large amount of 10-second YouTube audio collections covering several hundreds of sound events. For our experiment, we select 3 target events: dog sounds, baby crying, and gunshots. Those events have a good coverage of both long versus short time duration, as well as human versus non-human vocals. On the other hand, we also selected a negative audio samples, which has roughly 36K audios. And we split those data into train depth tests with 70, 10, and 20%. Given this labeled audio set, we also have another unlabeled data set, which is our in-house data collection. It's from the Amazon Instant Video ARV data set. ARV has the order of magnitude more audios compared to the available labeled data set. For our experiment, we used a subset of more than 5 million audio clips. Yeah.
Wrong label or weak label?
This is the weak label. We only know the labels for 10-second audio. And for the experimental setup, we extract the standard FB features, and we use a 63-layer dense net for our AED model. And similar as explained earlier, here we use the cross-entropy loss. We use the Brenner cross-entropy for each class, and we also sum across the different classes for the input for all the input audios. And we also have a weighting factor W here to balance the losses from positive versus negative training data, as well as from different audio classes. For evaluation, we plot the detection error trade-off curve, DET curves, which use force eject rate as x-axis, as y-axis, and force accept rate as the x-axis. And given this DET curve, we are able to compute the area under the curve and equal error rate numbers. As this computed from the DET curve, lower AUC and ER indicate better performance. For semi-supervised learning, a natural approach would be to do the self-training, which is simple, but it turns to be a very effective approach for different applications. The idea is that given this limited labeled audio set and large amount of unlabeled ARV data set, we could first train the model only using the labeled data set. From there, we could decode this model on the unlabeled ARV data set and only pick a subset of ARV audios for which our initial model gives high confidence predictions. We further infer the pseudo labels from the model's predictions to augment the training data and use it to update the models. We could run this process multiple iterations, but as you may see, there is an inherent problem with this process, which is there is no mechanism to prevent the errors made by the model itself. On the other hand, if the model makes some errors with high confidence scores, those errors will be added back as pseudo labels to further update this model. So that means after multiple iterations, this error may get even more amplified. Yeah.
Do you have any secret how you compute the confidence measure?
Oh, that's based on the output of the sigmoid function. A higher value would be indicated more confident. Yeah.
In the computer vision side, they always have like an image net to train, and then they adapt to that. Is there any value here to have the equivalent of to train on the entire audio set, and then start from there as opposed to scratch?
Yeah, that's a good point. We didn't experiment with that, but nowadays the pre-training has been very popular in computer vision, like LP side, and we are also considering something like that. To deal with this issue, we propose to leverage a classical tri-training approach. The idea is, given this audio set and AV data set, we first bootstrap the labeled training data into 3 partitions. From there, we could build 3 initial models using only the bootstrapped training data partitions. And for the next step, to update model 1, we first run the decoding of model 2 and 3 on the unlabeled AV dataset. We only pick a subset of the AV audios for which both model 2 and 3 have the agreed predictions with high confidence. From there, we kind of using the other 2 models to select or determine the labels for updating the current model. Similarly, we use model 1 and model 3's output to update the model 2, and likewise for model 3. After that, we have 3 augmented training data partitions. We could build 3 updated models. Here you may see in total we have 6 models. We could ensemble them to use their averaged output as the final predictions. And this table summarizes the performance for the approach I just described. For both measuring of AUC and ER numbers, the first column indicates the system trained only with the supervised audio set. The second column is for the self-training. Here we see that it may have some improvement, but it's not consistent, and sometimes it may give even worse numbers. If we move to the third column, which has the ensemble of all the 6 models from the tri-training, it clearly gives improved performance for our AED task. But here's a problem. As we ensemble 6 models together, during the testing time, it would take 6 times of CPU and memories, which may make it infeasible to deploy in the real-world applications. To deal with this issue, we leverage the classical knowledge distillation. And here we use the ensembled teacher models to guide the training of student models. And here, this alpha here is interpolation of the losses computed from the hard labels as well as the soft labels from teachers. And also the temperature T here is used to control the smoothness of the teacher models labels. By applying this knowledge distillation here, we get the 4th column. Here we could see that we could largely preserve the accuracy from the ensemble of teacher models, which still shows consistent gains compared with the baseline, which is the first column. Yeah.
The reason why you use the initial models in the ensemble is because the updated models ideally should be similar to the initial ones.
Yeah, that's a good point. We actually have an answer for that one. That's on this slide. We did some analysis using our data set to investigate the effects of contributions from the different approaches. Here, as you mentioned, we have ensembles, we have new data, right? Here, this is the supervised baseline on the label dataset, and here we first ensemble 3 initial models. And we see that from this ensemble approach that already gives some gains compared to the baseline. And then we only ensemble 3 updated models. I think that's what you mentioned. That gives further gains which tells the effectiveness of the adding more data from the ARV dataset. Finally, if we ensemble all 6 models together, that gives the best performance for most of the measures. Another analysis we did is we also changed the amount of pseudo-labeled data added to for model updating. And from our experiment, we found that 5K audios is a sweet spot for our task. We also did the analysis of changing the available labeled training data set. And here we gradually reduced the training data amount from the right to the left side. And we observed that the improvement of the training from the ensemble or from the knowledge distillation is consistent. Another approach we did for dealing with this data sparsity or data imbalance is we leverage an embedding approach. The main motivation is that we want to find the embeddings for limited labeled data to compensate the data imbalance. As here we have rare sound events as targets, and different target events may have different number of audios available, and the positive versus negative may also be very much imbalanced. A natural approach would be to insert a weighting factor like W, as mentioned earlier in the loss function, to balance the losses computed from positive and negative data, as well as from different sound classes. Here we also propose a embedding-based approach with to learn the embedding to dealing with the data imbalance. And for our experiment, we leverage a similar experimental setup, including the targeted events, features, losses, and metrics. Here we target a low resource use case. For our system, we use a single layer STM or 2 layers convolutional neural network. For this case, we assume a more strict restriction, that is, we don't have the unlabeled data available. And then the question is if we can do something better than only having the weighting factor in the loss computation for labeled data set. Here's the proposed approach. We want to have a embedding network epsilon here, which can be either STM or CNN. And we want to break these larger classes into smaller clusters, with each cluster has similar amount of audios as the other clusters for the same class, and also for the other smaller classes. And we want to learn the embedding in a way that when we compute the similarity between the embedding of the input audio xi to the centroid of the cluster it belongs to be larger than the maximum similarity between the input embedding as well as the centroid of the different cluster but belong to the same class, which in turn is larger than the maximum similarity between the input embedding as well as the centroid of the different cluster belong to the different class. By training this embedding and clustering system, we have a toy example here to show how it works. And this is from a synthesized data, and there are 3 classes in total. And the middle class has roughly 4 times data compared to the other 2 classes. After multiple iterations, we are able to separate the 3 classes and also break the middle class into 4 smaller clusters labeled in different colors. And we hypothesized that by doing this, the embeddings we learned from this clustering would incorporate the data imbalance issue and to be better used for classification purpose. This slide summarizes our algorithm of training this clustering embedding network, as well as adding another output layer for audio detections. I will skip some details, but for the second stage, we try 2 different approaches. The idea is that when we finish this clustering or embedding training, when we add the prediction layer, we could only fine-tune the prediction layer. But that's the first approach. The second one is we could fine-tune the whole system. With these 2 approaches, we get the experimental results summarized on these figures. We tried either STM or CNN as the embedding networks, and we have the blue curve as the baseline, which has the weighted cross-entropy loss computation. Here, if we use this clustering and embedding techniques, we have with 2 proposals. In general, we have the red curve and the black curve to be below the blue curve, which indicate better performance. Similarly, for CNN network, we also observe similar trends. And this table summarizes the equal error rate numbers. Another experiment we did along this story is we further have more imbalanced positive versus negative ratios, and similar trends hold. At the equal error rate, we typically observe the proposed approach, particularly if we fine-tune the whole system end-to-end. That would give the best equal error rate numbers. The next part is how we compress our models into to the smaller ones, consuming limited CPU and memories. And this also helps to improve the power consumption and also reducing the detection latencies. We also leverage a similar setup as previous semi-supervised learning or embedding approach for detecting these three target events: dog barking, baby crying, and gunshots, with similar data splits here. And knowledge distillation approach explained earlier would be a good approach of reducing the model complexity. Besides that, we also experiment with two other approaches. One is the low-rank matrix factorization. The idea is we want to run the singular value decomposition of the weight matrices, so that if one weight matrix has Q and P nodes in the neighboring layers, we want to insert a linear bottleneck layer with dimension R, which is initialized by the SVD. If R is carefully chosen, we could reduce the computations or multiplications from P times Q to P plus Q times R. This has been a very effective technique used for many speech-related applications. And we follow a existing literature that for the LSTM weight matrices, we decompose these recurrent connections and to get the singular vectors. And we share the same singular vectors to decompose the input matrix as well. Another approach we use to compress model is for quantization. And quantization refers to the technique of representing a floating point value with n base integers, typically n smaller than 32. And quantization is a lossy transformation. There could be a performance degradation if we quantize the weights or the input in a very low bit. So dealing with this issue, we integrating quantization into model training. And that is, we want the neural network to learn to correct the errors introduced by quantization. And this also helps bridge the gap between training and testing conditions. Our approach is summarized in these formulas. And here, given this input floating point, we first normalize it into a range between 0 and 1. And we select the quantized value based on the number of quantization bits n here. And for this neural network building, we quantize both input as well as these weight matrices. We also quantize all the matrix or vector operations as well as the activation functions. During the quantization training, the idea is in the forward computation, we use the quantized value to compute the neural network loss. And during the back propagation, we still want to use the floating point values for model with update. Considering all this knowledge distillation and SVD and quantization training approaches, we ran two sets of experiments. The first one is we compress a 3-layer LSTM AED network with 256 nodes per layer. For this set of experiments, we combined SVD and quantization training together. But there are a lot of numbers showing the three tables, but the main ideas, first we just ran the low-rank matrix factorization for the 4 precision matrix. And we select the dimensions to maintain a ratio of variance for each layer. And in this table, we observe that if we target for maintain roughly 60% of the variance for each layer, we are able to largely maintain the average accuracy compared to the baselines without any bottleneck. Another set of experiment is we also quantize the 4 precision matrix with 8-bit or 4-bit. And for quantization, we try two approaches. One approach is we only quantize the trained model for inference. Here we refer this as post-mortem PM. Another one is the quantization training as explained in the earlier slide. We found that if we quantize the network to be 8-bit, there's not much performance degradation for each case. But if we further reduce the quantization to be 4-bit, there's a clear degradation without training. If we compare this row with this first row. And if we're integrating this quantization to training, we can largely recover the performance degradation. Finally, we combine this SVD and quantization training together, which gives the final table. And the main conclusion is that for this 4-bit quantization training, with SVD of preserving roughly 60% of the variance, we are able to largely maintain the accuracy. And in the meantime, the model memory is reduced to less than 1%. Another set of experiments we did is to compress a deeper convolutional neural network with a 63-layer densenet to a single-layer STM with 256 units. For this case, we first tried the knowledge distillation. And we could find that here we measure both AUC and ER, and the first column is for the teacher model. And if we don't do distillation, we just train a smaller STM, there is a big performance degradation compared to the teacher model. If we run the knowledge distillation, we could get some recovery from the performance. And this table summarizes the number of parameters, the model size, and also the competitions in terms of the flops. We could see that there's a much smaller model for the single-layer STM compared to the teacher model with 63 layers. From that, we further combine the knowledge distillation and quantization training together, which further brings down the student model's memory from 1.26 megabytes to 0.17 megabytes. And with its performance to be largely preserved if we do the 4-bit quantization here in this column. Do I have another 15 minutes or 5 minutes? Okay. Sorry, any questions?
Quick question about the LSTM.
Yeah.
What's the reason for that particular kind of LSTM? Why do you use the same?
Yeah, here we're following a existing iteration of doing this. People at other places, they are doing this for speech recognition. My understanding is by sharing this component, that could be further saving some space of saving those singular values, singular components. But here we found that can be an effective approach of doing this, so we just maintain this approach. For the remaining time, I'll quickly go through another 2 projects we did. One is for medium presence detection. And the target is to recognize if the audio segment included median sound or not. For our experiment, this can be very useful for different use cases. For example, if we know a sound is coming from the median play, we could help reduce the false triggers, like Henrik mentioned, from the Alexa ads. We don't want to dash trigger Alexa devices. And also, this could help with analyzing the user patterns of media consumption for better recommendation purpose. For our experiment, we tried a context model of the detecting median sound. The idea is we know that the median sound typically lasts for a while. And if we could leverage some longer historical information for this detection, that could help improve the accuracies. Given this idea, we first built a local model architecture. That is, for our data, we have a recording from 30 seconds to roughly 30 minutes of audios. We chunk them into non-overlapping 5 seconds. We want to predict each 5 seconds having median sound or not. From there, we could feed each 5-second audio into this local model, which extracts the FB features as well feeding the convolution layers with residual connections and having another 2-layer of bidirectional STM with pyramid connections to make the prediction. But here we incorporate the contextual information to make it perform better. The idea is we could have a unidirectional LSTM, which takes the embeddings from the local models at every 5 seconds as the input and making the final predictions. We could also run this contextual model by taking into the intermediate representation of local models as input and feedback to the last layer of local model for making prediction at every 5 seconds. We experiment with these 2 approaches as contextual 1 and 2, and also use some facial normalization as a baseline. for incorporating contextual information. And our performance summarized in this table. Here we measure the dev set and the test set, ER numbers, accuracy, and F1 scores, etc. The arrow down indicates lower numbers are better, and the arrow up indicates the higher numbers are better. For this case, typically we find that the contextual model 2 gives a good performance for several measures. And as our training data has some missing labels, if we use this contextual model 2 to impute the missing labels to further update model training, that could give better performance for some cases as well. And this figure shows the false negative rate versus false positive rate for our testing set, and compare with this yellow curve baseline. Typically, our contextual model and with imputations gives better performance, which is lower than the yellow curve. For the last part, I'll quickly go through our SED research project on the spoken term classification. This is different from the weak word detection in terms that this is a simplified task. What we have is public data set with a audio clips roughly a second or 2 seconds, which contains the command words like yes, no, up, down, left, right. Or it contains the digital words like 0 to 9. And for our experiment, we have 2 sets of classifications. One is about the commands with augmented silence and unknown targets. The other one is digital classification with augmented silence and unknown targets. Our baseline is a couple layers with fully with convolutional layers, and this layer is for predictions. And this is for low resource applications, so here we don't have deep network. And a very relevant work published recently is to have 2 branches, and one branch runs on the full frequency band. The other branch has the non-overlapping subband and concatenate them together, and then further concatenating with the full band outputs for making final predictions. Different from this, we propose to have overlapping subbands together, which means each band we have some overlaps at the boundaries, and we combine these subband outputs in the first layer and feed it to the second convolutional layer and make the final prediction. Here, this figure shows both the commands classification and digits classification performance. We measure the computations using flops as x-axis and measuring the accuracy of our classification as y-axis. Here we could see that our overlapped subbands classification performs best in this low computational region compared to the blue curve baseline and the orange curve, which is combining of the full band versus non-overlapping subbands. And at last, I'd like to quickly mention another project in our larger team. And here our team is focused on the acoustic event detection, and my manager also leads projects for other applications. For example, our big team also has a group of people working on the emotion recognition in speech, and we plan to launch frustration detection for Alexa in the next year. And we also have some other emotion-related projects ongoing, but those are not disclosed yet. So I cannot mention exactly the details, but those could be interesting applications for improving people's life. And here concludes my talk, and thanks for all your time and attention and any questions. Thank you.
Semi-supervised markers. I'm familiar with co-training, but not tri-training. So co-training you have 2 classifiers, right? Now you have 3. Is it extension or is it something fundamentally different?
Yeah, as far as I know, this tri-training has been proposed like a long time ago, could be decades ago, and recently it raises more interest from LU side as well. We leverage similar ideas we want to have at least another pair of models to making a confirm predictions by comparing the outputs to make the labels more informative or more certain.
For training, you're simultaneously updating both and in training you have some that are continuous. They're just used for performance stuff like data structures.
What I understood, like what the person just asked, try training is kind of like an extension of core training. So why does it need to be? Have you done experiments on multiple core training?
Yeah. Here we start with simplified approach, which means if we have 3 models, we'll have another pair of models for validating the labels, as explained earlier. So having more models may actually help as well, but we didn't go further beyond that. Yeah.
So you were distilling from some kind of CNN to an LSTM?
Yep.
Is there any like hardware reason why LSTMs are favored or?
Yeah, we also got asked about the same question from the paper reviewers. The case is that we want to have a small model running our device, and for our case, LSTM is a single layer STM with 256 units, has limited memory and computations, and also is similar to our Alexa Guard system. Actually, as explained earlier, we have a STM running our device. So from that perspective, we are more interested in using STM as unit models.
You seem to be doing more and more on a device. Are there any legal restrictions how much you can do on the device? So that's something which is switched on all the time, right? And so initially, people were kind of happy that it's off until you say Alexa. Now it seems to be on for more and more and more, or doing more and more things.
Yeah.
So there is a temptation maybe to do much more, or especially also if the hardware becomes maybe less and less expensive. So there must be lawyers telling you how much you can do, right? I hope.
Right. If I get what you said, yeah, with some new devices, they will have better chance of supporting more functionalities on device.
Right.
That would certainly help mitigate the privacy concerns. I would say that's the main driving case for moving more stuff running our device.
Perhaps a different answer to Nick's question was a lot of these functions are not automatically on.
Yeah, you would hope that there would be maybe one legal restriction that you would have to switch it on. But you know, I'm just curious, really, what kind of guarantee there is that Alexa will not start doing everything, basically.
You mean not listening for them?
Without me asking, or without me permitting.
I think it has to be doing it that way. For example, for guard, people have to explicitly saying that Alexa turn on guard, Alexa turn off guard, so that we start to run. And even for record, it's listening to the record, but if it's not triggered, nothing happens.
Well, I'm sure you guys think about it.
No more questions. Let's thank Ming once again.
Thank you.
She is in charge of your lunch, and she's going to bring you back by 2:30 to 40. And I'll see you. So like I said,